When you open a browser, type google.com and press enter. The search bar appears in less than 50 milliseconds. To your eyes, it felt instant. To the physical universe, a massive sequence of hardware and cryptographic operations just fired across the globe. The moment your finger hits the key, your computer faces an immediate barrier. Machines do not understand domain names. They only communicate through numerical IP addresses. Before your browser can request a single byte, it must resolve this human-readable URL into a machine destination. Your computer first checks its local DNS cache in random access memory and its operating system hosts file. If the entry is not found, it dispatches a lookup request to your configured recursive DNS resolver, typically managed by your internet service provider or a public server like 8.8.8.8. If the resolver lacks a cached record, it queries the root of the global domain hierarchy, one of the 13 worldwide root name server clusters. The root server inspects the query, identifies the .com top-level domain, and directs the resolver to the .com TLD servers. The TLD server reads the Google label and responds with the IP addresses of Google's Authoritative Nameservers. The recursive resolver contacts Google's authoritative server, receives the final destination IP address, such as 142.25.0.19.0.46, caches it, and delivers it back to your operating system. This multi-step global lookup completes in roughly 12 milliseconds. Armed with the destination IP, your computer must transmit the connection request out of your local physical environment. Because your device cannot communicate across the internet directly, it must route through your default gateway, your Wi-Fi router. To transmit data across the local link layer, your machine needs the router's physical hardware MAC address. It inspects its local address resolution protocol table. If missing, it broadcasts an ARP request across your local network, asking which device owns IP 192.168.1.1. The router responds with its 48-bit MAC address. Your computer encapsulates the IP packet inside an Ethernet frame, addresses it to the router's MAC, modulates the digital ones, and zeroes into radio frequency pulses over Wi-Fi, and transmits it to your router's antennas. Your router demodulates the signal, strips the Layer 2 frame, inspects the destination IP in the Layer 3 header, and forwards the packet into your internet service provider's network. Here, Border Gateway Protocol takes command. Core internet routers use BGP tables to calculate the fastest autonomous system path, directing your packet through high-capacity fiber optic cables spanning continents and ocean floors, transmitting data as infrared laser pulses via dense wavelength division multiplexing. Upon reaching Google's Edge data center, your packet is directed to an available server. Before transmitting application data, both machines establish a reliable transmission channel using the Transmission Control Protocol three-way handshake. Your computer transmits a SYN packet containing a random sequence number. Google's server acknowledges with a SYN-ACK packet containing its own sequence number and acknowledging yours. Your computer returns an ACK packet. The connection is synchronized. Next comes cryptographic security via Transport Layer Security 1.3. Your browser and Google exchange parameters using the elliptic curve Diffie-Hellman algorithm. Google presents a digital certificate signed by a trusted certificate authority to mathematically prove its identity. Both sides independently calculate a shared symmetric session key. From this millisecond forward,